Okay, after a technical incident, we can resume our lecture. All right, so the last thing that happened here was we said that after the poly number of iterations of this compression procedure, we have either solved our CL, we have simulated our CL machine in polynomial numbers, polynomial time, or we've freed up a polynomial amount of free space. And to finish things off, we actually look at the statement of what we want to prove, which is that polytime bounded CL is equal to the intersection of CL and P. And so far, we've only used the fact that we have a CL machine for it. So now let's use the fact that we have a polytime machine for it. Once you've freed up polynomial number of free working bits, you can simply invoke the fact that you have a polytime algorithm and run it in the space that you've just freed up on your catalytic table. You kind of do the compression as many times as you need to free up that space. And now you can just use it as free space, compute your function, erase it all, and then go to the decompression procedure. And needless to say, the decompression procedure is as I described, just keep running it backwards to recover all your time steps. Well, that's it. Now, it should be noted that we dreamed this up like 5 years ago, but we didn't even think of using it as compression. This was an argument to kind of formalize this this idea too, which is it says that like you pick a random starting catalytic tape, then it will run in polynomial time. We wanted to see if that actually holds specifically for the random strings, i.e., the ones that are like have high entropy or whatever. And this was an argument to say that essentially, like, since you can get compression, either the time step has large entropy, or your catalytic tape has small entropy, the initial catalytic tape. And then this made its way through the grapevine, through some conversations at CCC and whatever, to a group working on derandomization. And then they kind of like came back to us and were like, "You guys are geniuses. You solved the problem." So that's how I got on this paper. This is the sum total of my involvement on this paper, actually. But what can you do? A little offshoot of this, kind of a bone to the meta complexity or TFNP inclined people, is that CL, we can get a slightly stronger upper bound in ZPP now. CL reduces to the problem lossy code. So lossy code is the following problem. I give you two circuits, C and D. C compresses by 1 bit and D decompresses by 1 bit. And the goal is to find a string where if you compress and decompress it, it's not recovered. This is a really nice problem that pops up a lot in meta complexity, especially in recent years. It's easy to solve in ZPP because a random choice up here will work. And this proof kind of says that CL reduces to this in polynomial time for the following reason. Everything that I just said kind of holds. This is a compression and decompression by 1 bit, and then compression by 1 bit and then a decompression by 1 bit if the machine fails to compute the problem. So what we do is for every tape that successfully computes the problem, this compression circuit just outputs like some trivial thing like all zeros or whatever. And then of course decompression will like succeed everywhere where this, where we didn't halt quickly, but everywhere where we did halt quickly, it just spits out some nonsense. And so what you get is that the result of any solution to this is a tape that ran in polynomial time, is a starting catalytic tape that runs in polynomial time. At which point your polynomial time machine just uses that as your starting tape and simulates it. So what's nice about this is that we know, we don't have any real strong leads on how to show ZPP is in polynomial time. It requires, some pretty strong hardness assumptions, but we actually do have some uniform assumptions under which lossy code is in polynomial time. So this is actually kind of another nice little bit of progress towards proving catalytic log spaces in polynomial time. So I think it's just worth mentioning that as like a aside for people who care about these kinds of problems. In particular, like all of this is sort of getting at the question of what does it mean to prove CLs in polynomial time. So this kind of says that there's a barrier to doing it.
Was it known that RL is also in lossy code?
No. ZPP isn't in lossy code. Lossy code is in ZPP.
No, the RL is.
Oh, RL, sorry.
Because it now falls.
Or
In fact, all of TC1 are just the lossy code.
it should be. You could just run Nissan's condition, I guess.
Okay.
I guess it maybe was implicit, but no one had saved it, or maybe some. I'm sure people have talked about BPL and lossy code because the same group of people care about these two problems. It's basically a circle of a couple of graduate students at MIT. So yeah. But anyway, this is a much more expressive class that we now know reduces to lossy code, so that's quite nice. And there's some follow-up, or there's some like discussions to be had here about how to extend it and whatnot, or what this might imply. For example, putting CL into the TFNP hierarchy, instead of TFCPP is like a kind of neat question. Okay.
Okay.
So I just wanted to mention that. I also want to say that this gives one direction of theorem 3 for free. So remember, theorem 3, as I originally stated it, is CL is equal to polytime CZPLP. Randomized catalytic log space, but in polynomial time. So one of those two directions, this direction is going to follow from derandomization. This direction is going to be a slight tweak on this. In fact, all you have to do is change the last step. So compression works exactly the way that it did before, but we're now not going to assume we have a polynomial time algorithm, and so we have to decide what to do when we actually compress fully.
Wait, but you have that algorithm, right? So
Say it again?
you just simulate the thing?
Exactly. So we know CL is in ZPP, and we freed up a polynomial amount of space, and we have access to randomness. Like, we're just trying to show that CL is contained in this thing. So once we freed up a polynomial amount of space, just appeal to CL as in ZPP, and run that in your remaining free space. Right? It's like if I change this thing to say the C, this thing go with ZP is equal to CL intersect ZP, which of course is equal to CL.
Okay.
Right, and really, actually, it's showing this direction because when I proved this theorem too, I actually proved one direction. I proved that this intersection is contained here. The other direction hopefully is obvious. If you have a CL machine that runs in polynomial time, then it both is a CL machine and runs in polynomial time. So nothing much there. Anyway, so that is kind of it for the preamble to derandomization. Any questions about how all of this works?
So why did we stop at ZPP?
Oh, yeah, you mean, do I put in something stronger here?
Yeah.
Sure. The problem is that you need to be able to, so fine, you can put like P space here. So CL intersects P space, of course, is CL. And then what happens on the other side? You need to be able to simulate the machine. So let's say, like you just don't get something interesting on the left-hand side of the equation, I think is what it comes down to. Like either you run a CL machine in polynomial time, or what you run P space, like that just isn't anything, right? Right. Yeah. Okay.
Okay. So theorem 1.
Yeah. All right. Let's do it. So I'm just going to talk for a second about what CBPL is without writing it on the board, just to clarify a couple of points. So as I've stated multiple times, CBPL is a catalytic log space machine, right, where we give it access to randomness. And the first question is, how much randomness? Well, since these machines can run for exponential time, they can have access to exponential randomness. CBPL machines are allowed as much randomness as they want, with all the usual conditions. It's read once, and they always have to hunt. In other words, they can't use their randomness to decide whether or not, or like, just stick themselves in an infinite loop with the promise that eventually they'll get a good random sequence that breaks them out of it. Nothing like that. A more sensitive question is, when do you have to reset the catalytic tape? If I get the answer wrong, do I still have to reset my tape? And the people who defined it, so Dada et al., take the safe route and say, yeah, you always have to reset your catalytic tape, no matter what. This seems like a more reasonable condition on the thing. A lot of the justification for this catalytic definitions is how they appear as subroutines in larger space-bounded algorithms, right? So if I'm running a traditional space-bounded algorithm for a while, and I fill up my memory, and then rather than just allocating new memory to it, I'm going to start using my old memory as this kind of catalytic working space. And then, of course, I'll get my answer out and then continue to run forward. So this is the framework that was used in some kind of classical results like STOC tree evaluation, which I have particular interest in.
Classical results.
As in on classical space, not STOC 2024 is classical in that sense. I'll give you that much. But anyway, if that's the case, then we don't, unless we're okay, just like saying if we get the answer wrong, then we're totally, we just get the answer wrong and we shut the whole thing down and we let everything break down. If we don't want that, then we really do want our catalytic tape to be reset so that we can continue to run our procedure thereafter. So you could actually justify not resetting the catalytic tape when the random tape gets it wrong by saying that if you're going to be wrong, you're going to be wrong. They don't really care. But it's nice to have this condition because it also allows you to say fortify your success probability. Right.
It's not obvious. I mean, and you could not amplify it, right? So suppose that
exactly.
You're wrong with probability 110. How do you get now wrong with probability 1/100?
Right.
Right.
You can't usually run the machine multiple times to take the majority vote.
That's not going to work here.
That's not going to work here because if you mess up your catalytic tape on any of them, your catalytic tape is going to be messed up forevermore. Yeah. So this is the justification in the NL rule as well.
I suppose you could justify something like the probability of messing up is negligible, like less than inverse polynomial for any polynomial.
Sure. So potentially you could come up with some definition where you're allowed, if your catalytic tape's messed up, you can at least attempt it. That your catalytic tape was messed up. It wouldn't be quite as nice, but at least, it wouldn't.
Yeah, but then
you wouldn't get consistency issues.
You really want. I mean, because in the end you want to use the algorithm.
Sure.
If it's a negligible probability of failure, that's still good.
Sure. Yeah, I guess that's fine. Anyway, those are going to come up implicitly today, but I don't think these conditions are going to come up so explicitly. I guess that the one about always resetting is sort of it happens throughout this, but I just wanted to kind of make it clear because there are a lot of ways you could define this class, and it's worth knowing which one it is. Okay. So. So the main insight of the paper is everything that we've been talking about before. The main work of the paper is kind of getting the easy case, quote unquote, to work out in CBPL. So CBPL, you also cannot have crossover of the configuration graphs. So if I fix a starting state X and I fix a random string, of course, everything is deterministic, right? So all the usual rules apply. But even if I fix just X and I don't fix the random string, it's still the case that as I run forwards, I'm never going to jump into another section of the catalytic tape for the configuration graph. Because again, I have to always reset correctly, right? Like here's the set of things that are reachable from this initial starting state. And of course, you run two end states, so everything reaches there. And here is everything that's reachable via a different starting configuration. And the point is, if there was any overlap here, then at this state, it's gonna go one way or the other. You know, if I fix my randomness from there on out, like I just get there and then I just see what happens if I fix my randomness from there on out, it's either gonna go one way or the other. And so, you know, there's some probability that one of these two states isn't reset. And that's no good. Now, one has to be careful. Reversibility doesn't work the same way that it did in the deterministic case. Because while you can't have things that intersect in a forward direction, you can have these bridges that I was talking about. So in particular, you know, here's my configuration graph for tau. And here's my configuration graph for tau. So tau. And this is based on a random choice. So this is a random bit comes up 0 goes this way, a random bit comes up 1 goes this way. And that this state is not reachable from either. In fact, it's reachable from no starting configurations. This can happen, and there's no contradictions that will occur. And what this means is that, for example, if I reach here, I need to be really careful about what I mean by resetting. If I'm resetting with respect to a fixed, if I fix a random tape and I reset with respect to that, then there's no problem. Right? If I fix a random bit to be either 0 or 1, it cuts one of those two edges, and so I'll run into no issues. But I can't just say I reversed writ large. You know,
You can't even remember what the random bit was, because it's readable.
yeah, so recall, we're going to be doing things in the sort of the compressor random world, where actually both my starting configuration and the randomness are going to be borrowed from the catalytic tape at some time.
So then you can solve.
Right.
But then you don't change the randomness. It's just that one. So it's either 1 or 0 at that point.
Right. If I'm considering one fixed random string, then it's either 0 or 1 at that point, and then everything behaves the way that it should. Right. So the first thing to know is that we do have a notion of reversibility. A notion of reversibility meaning, if I have a collection of random strings R, and I've been running one of them, and it got me to this state right here, then I can find my way back to tau. You get back to tau somehow. And essentially the way you do it is you just, even if you don't remember which R you're looking at, you can just look at every prefix of the first string and try and get home that way. If all of them fail, then you can try every prefix of the second string and try and get home that way. So on and so forth.
I understand. I did some simulations starting with top right. And I used one of these R's,
Right.
Right,
To get to this intermediate state.
So now I have this intermediate state, but I also have the R that I used to get there.
Yes. You might be remembering, and for most cases, you are remembering actually exactly where you are in the simulation. Like I know I'm using this string and I'm at this location in it. But let's see here. At certain points in time, we may not be remembering that information. Yeah, it's going to come up later in the argument. Nevertheless, if this collection of random strings is known to us, then there's no problem in getting back to the start state. Even if you've forgotten where it is, because you can just sort of iterate your way back.
Okay, so you know where you are in the graph.
Yeah.
That's your VI.
Yeah.
I call it. You just don't know how long it took.
Right.
Right.
And
but the randomness that was used is still there, just untouched.
Right.
Right. So the graph is reversible. So with this fixed randomness, the subgraph that only has this fixed randomness is reversible. And there's an algorithm that will reverse it. If you tell me the state VI, you give me the randomness, I can just go all the way back.
Right, exactly. And so all I'm saying is that we're not going to actually assume for this proof that we know how many steps it took to get there. For two reasons. One is the reason I just outlined. If you don't know where, which one you started with. Oh, so sorry. The main reason is because it may be that two different random strings actually bring you to the state at two different time steps.
Okay.
Right? So if I keep track of exactly which one I was looking at, then that might be, then it's fine to talk about like the number of time steps I that it takes to get somewhere. But it turns out that actually talking about the number of time steps that it takes to get here is not going to be the right notion. So this time step compression that we saw before, it's gonna take a slightly different form in this new group. For our purposes, it's not going to matter whether or not you know how long it took to get somewhere. So the reason intuitively why it doesn't actually matter that much whether you know how long it takes to run is that it could be that all of your, for every random string, you start with tau, this tau, and every random string brings you to the answer in a short amount of time. That would be fine, except that you still don't know that you've gotten the right answer. Right? We need to intuitively the case when your configuration graph is small is still the good case, but it needs a better analysis. Okay. Of course, if you do run for a long time, then you're good to go. Like if you somehow run this random string and you do actually take as long as it takes, then you could still do some compression. But it turns out we're going to do a different side of the compression instead. We're going to compress over the entire graph, not just one run, the run on one randomness, one random string. Okay, sorry. Let me say more. What happens if I have a ton of random strings and all of them take a short amount of time, but they all see different states, like completely tons of different states? I don't actually know I'm in the small graph case in this case, right? So like it could be that my random strings explore like this huge amount of area, which itself is in a much larger area.
But now by different states, we're talking about the position in the entire graph, meaning different tiles.
Yeah, different configurations.
Because I can definitely pick enough random strings R so that I will never see the same V.
No.
Or sorry, so that I will see repeated. Right?
Oh yeah, of course. I don't mean that like you never see the same states again in some like isolation sense. What I mean is just that each of them sees a sufficiently large number, sees a number of new states. Right? Every successive random string I run has some collection of has some collection of states that it didn't see.
By state, are you now including the tau or not?
Yeah, the whole yeah. You're only ever going to see one start, right? If I start in tau, in this tau prime, as my initial catalytic state, that will be the only start state I will see throughout the entire procedure. I'll always remain within this bubble, and I will never jump to another bubble.
Ah, so you're saying that besides, so in my simulating machine, I will have two parts of the catalytic tail. So in my simulating machine, I'll have two parts of the catalytic tape.
Yeah.
One of them will have some tau, which I'm going to use to simulate the machine I want to simulate.
Yes.
As the initial catalytic state of that machine I'm trying to simulate.
Right.
And then there will be some other part of the catalytic tape which will have some things which I will think of as randomness that I will use to simulate the other machine.
Yes.
Right. And so I will repeatedly do things like I will simulate the other machine starting at tau with one of these randomness, run it to some place that will give me some tau tilde, right? And then I have to undo, if I now want to do another simulation with some other randomness, I have to finish that.
Right. Or run it backwards.
Or run it backwards or something to get tau again, and now I can use another guy.
Right. Yes. Yeah, exactly.
Very good.
Yeah.
So actually, only one of these bubbles is at play.
Only one of these bubbles is happening.
So if I'm looking at all of the possible configurations with all the possible starting states, right?
Yeah. I just mean, this diversion was just to say, you need to be careful about what it means to reverse, because if you don't take into account these like bridges and whatnot.
Can you write a little square with tau prime and tau or whatever? Well, but that's part of the catalytic.
Oh, yeah, sorry. So my catalytic tape is going to look as follows. It's going to have something tau, which, as you say, is going to define which bubble of the original machine I'm in. And then after that, it's going to have a large collection
Of arms.
of arms. In fact, 1, 2. Right. So this is sort of doing like kind of how I drew on the board before. You have BPL is in CL because this was what you use. Now when I want CBPL is in CL, I mean the first thing I have to do is kind of stick the same tau. Right.
All right. And now, okay, so now let's see. So now we're kind of exploring this. Now it's not tau prime, it's actually just tau.
Yeah. Sorry.
Right? So now we're exploring this bubble of the original machine.
Right.
And what do we know? We
Good.
know that for most R's, if I start with this tau and I explore the bubble, I'll end up in a guy that has the correct answer and has tau again. All right, we have as much time as we Why don't we finish?
Okay, so actually, so let's take a step back and look at like remember the whole intuition.
Give me like an overview. So
Yeah.
So there will probably be some situations where these R's are bad, right?
Right.
And what you want to do is you want to detect whether your family of R's is bad, and if it is, you're going to compress it and then use the freed up space.
Correct.
Good. Otherwise, the families of R's is good, meaning if I simulate my original machine, the walks that I get on this bubble with the different R's, if I take the average, right, average answer, it should give me the right answer.
Yeah, so good. Yeah, thank you. Good. So when is R good? It turns out you need 2 conditions to hold. The first is that the bubble that you're in, let's say, sorry, tau comma R. Right, tau comma R is good when 2 conditions are fulfilled. The first is that the bubble that you actually started in is small, right? Config from tau is small.
That only depends on.
That only depends on tau. Yes. And the second is that R explores config graph from tau.
Well,
That
whatever that means.
yes, exactly. So remember, in the BPL case, we had a very the first one came for free. We are in a BPL machine, we are in a small configuration graph.
Yes.
The second one followed by Nissan's condition. This was exactly what it meant for your random collection to explore.
And okay, so let's suppose that by miracle, the tau is actually small.
Yes. In fact, let me actually interject and say that it was known that CBPL equals CL under a derandomization hypothesis. Now, while that sounds like trivial in terms of actually just getting the randomness here, it isn't, because you might need a exponential amount of randomness, and this you won't get from your PRG. What did you use your PRG for? You actually used your PRG to jump into a good bubble. So you took the output of the PRG and XORed it with your initial catalytic tape. This is something that you can undo later because it's a PRG. You know, it's not a source of real randomness. And then that was used to actually guarantee that you started in a small region of the graph. Furthermore, they then used it once you had that to explore the small configuration graph level.
So now let's suppose that we already miraculously have a tau where the bubble is small.
Correct.
Now there should be an Nissan-like condition on the bubble, right? Which just says something like, if I reach some V, right?
Correct.
The amount in my set R, half of them go on the 0 direction, half of them go on the 1. And that should, like as before, guarantee that my probability, right, these are kind of the same probability of accepting as a truly random tau.
Yes.
Right? Assuming that my bubble is small.
Right. Now notice, even though that is true that this Nissan condition holds, it's still, you can't enumerate over all the states unless you knew what all the states were. If I had a list of all the state sigma that I could actually just, write down with log n bits, like a mapping from log n bits, which is which state it is in the list, to the whole catalytic state, that maybe then I could do a Nissan condition and test it out. But now we're like really stretching. So it turns out we're going to need to bring in some heavier machinery here. We're going to bring in some generic machinery for when R is a good collection of random strings. We need one more author. So this is where the Nissan
Suppose I know the number of these guys.
Sure.
Then it will be fine, no?
Tau changes.
That changes the number.
You would need to be able to map, you have to be able to map into your catalytic tape. You just have the number and then you overwrite your current catalytic tape with whatever that outputs. That seems like also kind of document, right? Seems like you would need to actually be looking at tau and then output the tau I or whatever.
The VI in this one.
Yeah.
I need some way to enumerate the VI. So
Exactly.
That's not obvious. But in the BPL, I could, because it's just,
Because you have
content, it's the content.
Correct. Now, this is where I suspect that there are easier ways to do this proof. Kind of since this proof has come out, we've found some nice things to do. For one, James found a really nice algorithm, which I described to you guys yesterday, about how to take random, guaranteed good random walks over a BPL graph, even if you don't get good randomness, even if you get no randomness whatsoever. You can still kind of cheat your way into random walks. That might work here. Another trick is hashing. If I know this graph is small, then I could just hash, come up with the right parameters for a hash function, so I know everything in there is uniquely hashed, and then run Nissan's condition from that. And how do I do that? I basically take all walks, somehow take all the walks that I need to in the graph, and for all of them, I check whether or not you actually have reached this hash value. You'd still need a way to enumerate all your walks in the graph, which I haven't told you how to do. But I think some combination of these ideas could potentially still work to get it to you. We just went straight for the kill. These guys, our co-authors are real experts at the Nissan generator. So why do more work than you have to do?
Okay.
Yeah. So these random strings are not actually going to be the walks that we take. They are going to be the seeds that power the Nissan generator.
Okay.
So what is the Nissan generator? It's a magic box that does literally everything you would ever want it to do, is essentially the only way I know how to say it. So Nissan takes two seeds in some sense. In fact, we think of one of them as the seed of only logarithmic length, and the other is, I don't even know what you'd call it. Just the description, it's a source of randomness, essentially. So Nissan R is a function that sends order log n bits to to polynomial bits. Once I've hardwired in an external source of randomness, and this thing is going to have poly bits itself.
Possibly more.
Parameters. There we go.
Right, and these Boolean bits would be more than?
They're large. It's a very large number of Boolean bits. But the key for this is going to be that we don't assume that it is actually true randomness, because the Nissan generator has the following nice properties. You're in one of two cases. One, Nissan of R is fools all distinguishers. Fools all distinguishers. Now, these will be distinguished in some class, which we'll figure out. In our case, it's really going to be once computable in catalytic log space. I think this really goes up to all polytime distinguishers without trouble. So that's case one. Or two, we can compress polyands from the parameter R, given access to the fooling distinguisher.
The unfold.
Yeah,
You're saying for a single R, it pulls all distinguishers or
correct. So for example, think of R as being, if it's a random string, think of it as being like a random truth table or something like that. Like it's the random truth table of some function where on the log and bit inputs. Like this thing is gonna fool all distinguishers as random, right? But the point is that if that's not the case, if it's less than a random, if it's not a random string, then think of it as like the truth table of a function which has a much smaller circuit. Right? That much smaller circuit could act as compression, for example. And that is, you know, Nissan-Dickerson does work with these kinds of ideas in it. And a nice recent addition to the whole literature is that some of our co-authors on this paper showed that this thing is in logs. It can all be done in like logspace. So the Nissan-Dickerson generator is now very space efficient. The distinguisher is actually what we're going to use as a different object called a previous bit predictor. You've heard of a next bit predictor, it's from Yau's whatever. It turns out if you just turn it to predicting the previous bit instead of the next bit, it does incredible things in the space-time world. Don't ask me why.
What do you mean the previous?
You get access to like xi plus 1 to xn, and you're trying to predict
No,
things.
but it's the same thing.
It's the exact same thing. But the important thing is that when these are like the source of your random walks, it actually matters whether you're taking a walk forward versus getting there. So transaction in the previous bit predictors does a lot. It does a lot of work, in particular, to make all of this space efficient and be targeted towards randomness.
I see. I mean, so the generator and the decompressor doesn't go, right?
Yeah.
But you're saying that if I apply it in the other direction, that actually helps in this random walks context.
That's it. Sorry, no, thank you. Yeah, that would approach you to whatever 2.5 hour merge.
Yes.
If mental drop off.
It's actually 1 p.m. We could pause. We could
I
go
mean,
for lunch.
It depends on how many more ideas you want to explore in this, because this is really, I mean, this basically acts as a black box for the good case. Like this, assuming your configuration graph is small, your distinguishers that you're going to test it on essentially are just going to be like, it's just going to be asking essentially what you have, like what you have or haven't seen, whether or not you have or haven't left the reachable graph from some parts. We can dive into the technical details, but essentially Nissan-Dickerson, if you set things up correctly, is just taking care of number 2 in a way that is expected. Falls from previous works.
So you're saying that my distinguisher is going to check. So you're giving me, so now the R is the output of the Nissan-Dickerson generator.
Yes, exactly. So right, this is now going to be like, we'll call it W for that.
Okay.
Right, and WR is just the output of Nissan-Dickerson the algorithms. The collection of blocks that you get out of there.
No, but that's capital WI. That's capital WI, right? So now that's my understanding.
Oh, yes, capital W, yes.
Capital WI. So now each RI is going to be fed to the Nissan-Dickerson generator that outputs a collection of walks WI. So actually these WIs are this capital R that we used to have.
Yes, exactly.
Right? Each WI is like a capital R like we used to.
Okay.
In fact, we're gonna end up having a lot of these specifically just to hack around. Like we're actually gonna pay all attention to one of the WIs, and that will serve the purpose of our R. We're gonna use the rest of them essentially to power distinguishers, because when we do compression, we suddenly lose access. Like we compress RI, we lose access to the distinguisher if the distinguisher is actually based on the walks of the generator. Like you get some kind of cyclic reference. So in reality, what we're going to do is we're gonna call the entire configuration graph that we care about to be the union of all of these WIs. And then we claim that by the pigeonhole principle, there's one particular WI which is completely subsumed, whose walks are completely subsumed by the walks of everything else.
Subsumed by the others.
Right.
So
So there's some WI which is redundant, essentially. Like one of the Nielsen-Dickerson outputs doesn't bring you anywhere new.
Okay.
Assuming your graph is small enough.
Okay.
Right. And now in this case, you can use essentially WI is going to take the place of our R originally. And the distinguisher is going to be using WI prime. I cannot do that. So in reality, we don't actually need all of this. We don't need all these extra ones for like as you observe, one of them alone is enough to be to serve as our R. Everything else is just for making sure that we can actually power the argument.
So you're saying if the configuration is not small, you can use the trick you've already shown us.
Yes, so in fact, so that is the last step. The last step is what happens when my configuration graph isn't small. What happens when these WIs themselves explore too much of a region? These union of WIs explore too large of a region. And what we do in this case is it's not quite time step compression, it's just enumerating over the number of states that you've seen. So the first thing to do is show that you can actually like check how many different states you've explored. And the way to do this is just literally comparison. So if I've run, here's my list of random strings, and I run up to this point. So I've run all these random strings. I want to check, am I seeing a new state now? What do? You just check bit by bit how it compares to everything else, every other string.
You rerun all of the previous.
Correct. You at every step in time, you're going to rerun all the previous computation you've done just to figure out if this is a new state.
Okay.
Yep. It's a really, really obnoxious procedure, but it is what it is.
So you've got an enumeration of the states in the box.
So obviously the very first time step that you take, you're going to see a new state. The second one, you're going to see a new state. In fact, everyone along this path, you're going to see a new state up until the point that it probably prematurely halts, and then you could ignore the rest of these. So all of these are new states. But now the question is like, is this one going to be a new state? Well, what do? You go back and compare it to everything you saw here. What about the next one? What about the third?
Now, okay. So now this gives you an enumeration of all the states that all the W's except this WI traverse.
No, actually, no. We're first going to check to see how large this entire union is before we even bank on there being a small one. Because if this graph is huge, the original principle doesn't work. So first, we're just going to check how many different states do we see across all of these. And if that
is very big, then you're going to use this, right? That's what you're saying.
if it's very big, then we use the argument
trick.
right? I write down the I trick. But if assuming that we explore a very small region of the graph via all the walks, now everything I described goes in. Now we're going to use this to figure out a small one using the exact same comparison procedure to figure out which of these is subsumed by the larger. Okay. Now this is going to be my set of random walks on which I can apply the Nielsen-Dickerson generator and use a distinguisher that says essentially, do these walks like the global set of walks, defined by this large thing.
Wait, how do you?
You got a WI.
Oh,
You're either gonna compress it or
Hmm?
even once you find this WI by the pigeonhole principle, now you need to check if it's 1 or 2 in this
But you need to check if it actually explores your graph well, essentially.
no, but
which is this thing as fooling all distinguishers.
what if the tau?
We actually just pick a good set of distinction, but yes, go on.
What if tau is large, but your WIs don't explore all of it?
That's
Oh, you mean the whole union, right? Okay,
The
good.
union, yeah.
Yes, so so I actually misspoke just a couple seconds ago. Your distinguishers,
The bubble is big.
right?
Okay.
So your distinguisher is as follows. So remember, a distinguisher should distinguish randomness from what you've got. And what you've got is the walks in this WI specifically.
okay. Fine.
right? So your distinguishers, you're gonna have two distinguishers. Let's say that, so here's tau, right? And here's the set of things that you reach via walks in W. Tau, so here's the walks in W, and here's the bigger set of walks, right? The problem is when this thing is tiny and this thing's big.
Yeah.
The first distinguisher is, does your walk stay entirely within W?
My walk.
Yeah.
Sorry, W, which walk?
Right, so it's a distinguisher, it's supposed to distinguish the walks in W from random walks. And the first question is, does whichever walk you give me actually stay inside this bubble? It doesn't have to be a walk from W, but it has to stay inside this configuration. Right?
Yes, what do you mean? I see. So a distinguisher is what? Is something that distinguishes this set of walks W from a truly random walk.
Correct.
So what you're saying is that if W is much smaller than tau, then a random walk is going to escape
Right.
W,
Exactly.
right? So my distinguisher, what will it's given me some random bits, which will, or a collection of walks, right? Which is truly random.
Right.
So I just run these walks starting with tau and I see, do I get a state outside of W?
Right. Do I ever leave this this bubble?
And what you're saying is that if W is actually much smaller than tau, then this is gonna happen. So this distinguisher works, and then that would allow me to compress the R that generates.
Exactly. And the important thing is you need to be able to recognize this bubble. Right? And to recognize this bubble is where this whole pigeonhole argument comes in. Oh shit, sorry. One more time. This is the union. Okay, yes, there we go.
Okay, that's also easy.
Sorry. This one's the union. There we go. Good. Right. So this is the union of all of my walks across all Nissan-Bickerson generators. But what we're trying to do is distinguish only the one WI that falls in the middle here.
Okay, I don't know about the middle. Now I'm just worried about the union not covering all the towns. Now,
Not covering all.
not covering
The
like,
bubble.
yeah, the whole block,
Yeah,
or like
that's
a
what
huge
we-
fraction of the vote.
Right.
But I've understood that you give me an argument why, if you give me just a single W, which would be in the image of the Nissan-Bickerson generator, why, if just a single W doesn't cover like 99.999% of the bubble, then my distinguisher is gonna come, and it will with probability 0.0001% at least.
Right. So sorry, the whole union, I'm actually gonna take the whole union. I'm sorry. It's been a while since I did this.
No, but the distinguisher is made to distinguish a single WI from a random WI, right?
Yes, right. So, okay, why don't I just write this down specifically?
But what I understand is now I can get my hands on a family of WIs, all of which cover 99.99% of the value. But how does that stop? Sorry. What does this distinguisher need to do? I give it an image of the
Right.
generated versus a random string.
Right, so no, so. You agree that we can test this property, right? If I give you a walk, you can test whether or not it stays inside this union.
Yeah.
Right, now. This specific walk, set of walks, WI, the image of this specific Nissan-Bickerson generator is totally contained in the union of the rest. That was the whole point of this pigeonhole argument. So, if I get Nissan-Bickerson on WI equals Nissan-Bickerson of its little WI,
Yeah.
or little R, yeah, implies that this one equals 3. Right? Every state that is explored by this WI is also explored in the rest. Means this thing is contained there. Whereas a random string, if this whole union doesn't do a good job at exploring it, this whole union can fall outside. So that's what I meant by this thing powering the distinguisher, but we're going against this thing.
Oh,
Or do I said it wrong?
so that means that I now have a collection of WI. I have now a collection of WI, and you claim that there has to exist. Right, and if a random walk escapes if a random the random walk, a truly random walk, instead of Wi escapes the union of the remaining.
Yeah.
Well, that means that the union of the remaining isn't covering all of town.
Right. And in particular, you want to compress that union because it's not random. But since you can't compress the union, you're just going to compress the specific WI. You compress the specific WI, and now you have full access to this distinguisher at every time. Yeah, you compress all of that. Yes. That's distinguisher one. Distinguisher two is even stupider. It says, assuming you stayed inside this union, did you hit 0 or 1?
It now guarantees that the union of the WIs covers all of the power. Distinguisher one. Oh, distinguisher two is. Even distinguisher one is true, meaning, yeah, it's.
That you stayed inside your set of walks.
You stayed inside your set of walls.
Did you get a 0 or 1 there?
What answer did you get?
Yeah, literally, did your machine answer correct? Like, did your machine answer 0 or 1? You're going to hit a halt state if you stayed within this, because every walk inside this halts. Oh yeah, that's a subtle point that I guess I didn't mention earlier. If one of these walks, if any of the walks inside this whole union doesn't actually halt, like come up with 0 or 1, then the number of states you've seen along this path alone is so big that you can do this that compression, which means all of them halt. Which means if you run a random walk, either you stay inside and halt, or you go outside.
Right, you go outside, you're done.
Right.
Distinction one. Now suppose you stayed inside and
Right.
halted. What answer did you get?
Right.
Well, I see, so I see.
This is just making sure that you're actually behaving correctly.
I see, so if you got a different answer than a random walk.
Right.
Right, then here's your distinguisher, now you can compress it.
Yes, good. So assuming that both of these distinguishers actually don't distinguish WI from a random walk, then WI is a good collection of random strings, and you take your majority vote. And if either of them fails, then this is we can use this distinguisher to do compression. Now, to show that like if both of these succeed, that you actually get the right probability, you have to like do some previous bit predictor YAO stuff, like just the usual, making it all work out.
And I can check, right? And I can check, so I understand distinguisher one, I can check, I just I run all these walks and I see if they're inside, and if they're not, this distinguisher.
What are you checking?
Right, but you can check you can check whether you stay inside. If I give you a walk, you can check if it stays inside this, and you can check if it gives you a 0 roll.
In CL.
Yeah, if I give you the walk, you just run it forward, write down the answer, like does it leave or does it not, and then run your machine backwards for this fixed walk.
Right. Why does
You can reverse for the fixed walk.
oh okay, the distinguisher gets randomness somehow. It's okay.
Right.
It doesn't need to generate.
Wait,
So in order to turn this into an actual like an actual compression argument, like to test what these probabilities are, you have to do again, this is like now plugging this into more classical machinery. Like you say, you use these distinguishers to try and do to power a predictor of 1 bit, enumerating over everything that you need to make this true. And you check the bias of that 1 bit.
I don't understand. So what does the algorithm do? So I know how to construct these levels, got it. So step number one, I will
Find the states.
go over all I and see if there's an I such that the walk WI stays inside the union of all the others.
Right. Which
So
is something
that's
that no, it's, okay, if you start by counting the number of states that you explore in the union of all WIs, and that thing is small, then you know that this is true by the visual principle. Because the number of this time step, like the number of states that you're gonna see, is much smaller than the number of W's I'll give you, the number of R's I'll give you.
Oh, I see. So step one, I see. So step one, I run over all these walks, I count the number of different states that I found.
Yes,
That's
exactly.
step one.
That's step.
Suppose that's very big. I use the I trick
Correct.
to get some free space.
Yes.
Good. So now I know that all the number of states that I found are small.
Yes.
That could be for one of two reasons, right? Either the bubble is small and I've explored all of it, or the bubble is big and I didn't, I stayed stuck.
Yes.
Now, if I stayed stuck, that means that my collection of walks is not pseudo-random.
Right.
Is it really for the size of the bubble? What if like with very small probability you get out of this and walk for a really long time? The bubble is big, but with high probability you're not going to.
Then you will still not, your random walk won't leave this. So
Yeah, it
yes,
won't.
it's true. It's not guaranteeing that you're actually in a purely small bubble tau. It's saying that the bulk of the mass is on a small bubble.
Sure.
So because I mean, I'm the adversary, I can choose the RIs, right? So suppose I've chosen the RIs so that all but one of them artificially stay in a small sub bubble
Right.
of your large bubble, right?
There exists a
So, right, and now I look at the other one.
So now there exists a distinguisher.
Right. So you can see, so I mean, if you pick these, even if you actually, you have one of these RIs is good enough to take random walks. And another one is good, bad enough to compress. Now I'm just in a doubly good situation. I ignore the fact that, I might pass up the fact that this one does take good random walks, because if I can compress a polynomial amount off of another one, then I've already won.
Sorry, yeah, but I'm still lost. Okay, so suppose the bubble is big, but I artificially stayed inside of it. Now I agree if I were to run a distinguisher on this WI, which is artificially enclosed.
Yep.
Versus a random walk.
Yep.
The distinguisher would distinguish.
Right.
Right. So that should mean that if I now take, and I know what this distinguisher does, right? Because I have the algorithm for it.
Right.
So and I plug it into the decompressor. Oh, is that what you're gonna do? You plug it into the decompressor and you check that the decompressor actually, what? That the compressor actually compresses correctly RI. Is that what you do? Because you never toss randomness, right? So
No, sure. Actually, there's something going on in the middle here, which is just that if I tell you that this distribution is easily computable and fools it, then you get this all to work. And it turns out that there's an extra step in here, which turns any potential distinguisher into a predictor. And the predictor can be actually you can compute its in log space. So you can actually test whether or not this is going to, whether or not these two distinguishers work. But that is the extra step on top. So like, I have the paper here, we can go through it, it is pretty ugly.
So, no, I think
You can actually test whether your distinguishers can see it.
Well, no, really what it is you come up with a predictor, which is some artificial looking thing where essentially you take a walk, a pseudo random walk up to some point, and then you take a purely random walk after that, and you you XOR it with a random bit.
Yeah, that's
So you-
Gauss predictor arc.
Yeah, exactly. And then you ask the question like, what's the bias of this bit?
Yeah.
And it turns out that if the bias of this bit is high, then your distinguisher is fooled.
So we can compute the bias of that.
Yeah, you can compute the bias of this thing. So
It's just a small walk.
yeah, essentially, like if I give you access to all the yeah, so what do you actually end up needing? You need to know the bit. So you need to enumerate over all choices of the bit and all choices of this would be the state itself. Each second. Oh no, V is the collection of all this written. Right, so you need to enumerate over this XOR bit B, you need to know which Nissan Dickerson, you're actually running. What K. You need to know what the seed is, so this is the pseudo-random walk taken by GK of S. Sorry, G sub K. Oh. Nissan Dickerson of R sub K. Of S. And you need to run this for like L1 steps, and now you can run this for L2 steps. And so your predictor is going to predict the bias of the bit over all choices of K, S, L1, L2, and 3. Like in the Nissan's argument. So this is for a fixed walk afterwards. So this is the random string. I already used R.
But we go over all of them.
Yeah. So you have this fixed string gamma, and you want to compute the bias of this of all of these things. Like for every fixing of these, there's going to be a different predictor, and you're going to use this to try and predict. This is K or gamma greater than or equal to L2, or let's call it greater than L2. And you want to actually be predicting gamma L2.
I think I'm starting to understand.
Yeah.
I think I'm starting to understand.
This is just an ugly way of turning this distinguisher into a predictor.
Yeah, so you have this distinguisher, right? So from this distinguisher, yes, indeed, you can obtain the next bit predictor that will work on one of the positions of the doubles, of the R's.
Right. If this is a good distinguisher.
Right?
No. If these are good distinguishers, then you can actually use this to do a previous bit predictor.
Right, it should be the R. No?
Oh, is it the R itself?
Well, that's what you ultimately want to compress, right?
Well, if your previous bit so if your previous bit predictor works, then you should be able to plug it into this step and get a large compression out of it. It's not just one bit, it's going to be like a lot of bits.
Oh yeah, it should be like 2 to the size of x or something. Bits, and it's not that you can predict them exactly, but you have an advantage over random guess.
Yeah. No, it's yes, it's not a perfect prediction.
I see.
But as long as you don't have even like a slight bit amount of advantage, then you can prove that overall these distributions are both basically they're not good distinguishers, and thus that you take good enough random walks. As long as it's a really, really small bias. But even a slightly good enough bias is good enough for some bigger set, and let me just yeah, we're going to be using this on the outputs of. I think you're using this on the outputs of this one. The WIs that you're actually trying to compress. I believe you're correct.
No, so you can predict one of these poly-n bits. What does that mean? You can predict it over, right, the choice of S. That's what I remember, right? So in the Nissan generator, you assume that knowing all the previous bits, you can predict the next one. What does that mean, predict the next one? That means I can predict the next one. I should in the end get some algorithm to compute this ith bit given S, right? S stays free, right? So
what is S? S is the seed.
S is the seed,
Yeah.
which is log of whatever bit. Right?
Yeah, right. So that's all fine. The reason I'm fixing the S here is because the like you're taking a walk using a different Nissan-Dickerson thing. That's like this, the pseudo-random part of it. And then you're on the second part, you're plugging in either a random string, a truly random string, or a walk from, you know, what's it, W. And this thing you can range over all possible seeds.
Yes, yes, exactly.
Right.
Yeah, so each bit of, right, so overall possible seeds, right? So what
Yeah.
is WI actually is
Is
I
the
run the
union of
Nissan
all
Dickerson generator. For this RI, overall possible seeds.
Yeah.
I guess what I want is something like each seed should give me one walk. Right? Each seed should give me one walk.
Yes,
And
yes,
so-
each seed gives you one.
Right? And so predicting one output bit here should mean that there's a particular bit in each of the walks that I can predict, meaning
Mhm.
by predict, I mean I give you the index of the walk that I want you to give me the bit.
Yeah.
And the predictor will say with probability better than a half, strictly better than a half, what that bit will be.
Yeah, it's this L2 parameter, but yeah. Yeah.
Okay.
Yeah, and again, they're doing previous bits as opposed to next bits, like this is your string that you're testing. Again, it doesn't matter for the whole for most of the arguments, but it does matter when it comes time to say. That actually this is good enough to guarantee.
I see, so your collection of walks is actually, for each seed you have a walk.
Yes,
What's the length of the walk? That's the length of the output of the Nissan generator.
right, although probably it's gonna be shorter than that, because you're gonna hit a halt state before that.
No, sure, but I mean, let's just think of the walk
Yeah,
as
yeah.
all the random bits you might use.
Yeah, exactly.
And then suppose you have a distinguisher. What does the Nissan proof tell you? It will tell you that there is a position which you can predict if you know the previous positions. Right? Knowing the previous positions is just knowing the random bits of all the walks of the walk, right? Up to that point.
Yeah.
And by predict, what does that mean? That means that I give you the seed which selects which walk, and you will tell me 1 or 0, and you're going to be correct. Probability is strictly bigger than a half.
Correct.
Right? But being correct with okay, good. With probability strictly bigger than a half. So here's how I can compress the actual value of the walks. I take this string of length 2 to the size of the seed.
Yeah.
I just take the string which the predictor is going to predict, right? And it's correct most of the time. So how do I compress the string? I just have to say in which points the prediction is wrong, right? And that's the compression of the string.
Yes.
The predictor, so right, because this, so right, it's really,
Yeah.
Let me get drawing. I think I understood.
That's what you understand about the pace on vision.
It's like, so what is your collection of walks? Collection of walks is just the random bits that the CL algorithm is going to run you, right? And I'm going to, so each collection of walks is derived from some C RI to PRG, right? This right? And now, how many walks do I have? I have as many as these strings. So I have C as 1, that's polynomial, right? And I have, and then, right? And what is this? This is the Nissan regression on I x 1. Yes.
Yeah. Exactly.
Okay. Okay. So what does the Nissan regression theorem should tell you? It should tell you the following. So suppose that I have an algorithm D, right? Which will have different behavior in the following 2 scenarios. Scenario 1, I choose one of these and I give it to D. Scenario 2, I choose a completely random string of the same length and I'll give it to D. Then what does this theorem tell you? It'll tell you that if you have this distinguisher, then there's some algorithm that uses this distinguisher as an oracle. and there's some position I such that this algorithm, if it will need to be given, it will need, so this algorithm on input I and WS up to I, right? So it's algorithms given the position I and this second W, oh, we're using I given J and WI for S for S up to J will equal to W I of S at J with probability strictly with a map, right? With some,
yeah.
Right? So that's what the disambiguous will tell you. Good. And what we're assuming, so we're supposing that we're getting a distinguisher, right? Good. But then I claim, so now what are these, right? So
You can compute these and check the correctness of the predictions.
let's check. Yes, so yes. And what are these actual bits in the disambiguous sense generated actually? Is the following. You have your Ri, and you think of this as a Boolean function, right? And where did these bits come from? This Boolean function, right? Is a function on S on the S, right? And these bits are obtained as follows.
You're going to the workings of the
J bit is a copy of F applied to some of the bits in S. This is the J bit. Right, that's what it is. Right? That means that this column here is actually a selection. It's like you take the subcube, right? So this is the subcube on 2 to the S, right? And you take a subcube on it's a subcube on S bits, and you take a subcube on however many bits F is given. So it's a section. Good. And what does the predictor give? Right? The predictor is going to tell you, given these values, it'll tell you what these values are. Right? So it should somehow, so the predictor is going to predict something that should be here.
So this is justification for why you can compress R.
Yes, why you compress R, because what's actually in your pick is R, right?
Yeah.
It's not this
Right.
is virtual. Right? Yeah. So, but that should be the point now, right? That somehow your predictor, knowing it should be like this. You have your
You can compress.
So then it's able to output that string again, given the rest of the RI or given us
Given the rest of the
distinguish, given everything else, including the distinguisher itself,
Right, so
first the R,
exactly,
etc.
exactly. So A gives the distinguisher to be able to turn this into a prediction of what these values are.
You build the same predictor, it gives you more than half of those.
Right. In the original argument, actually, it's somehow there was some non-uniform part here, so you have to fix that, right? Because you don't have this. In the original argument, it's not big distance. You don't have an activity, right? And remember, you need to now fix. I mean, you need some help. This is a non-uniform algorithm, but I'm guessing it can be made uniform with some.
Yeah, it probably depends on the strength of your predictor, or what your predictor is computable in. All of these are computable, just like catalytic logspace. They're really pretty easy.
Right, and that's okay. So now your predictor giving everything but R will predict these bits. So here's what you're gonna do. But it might be wrong a little bit, right? So
That's fine. Yes, you can just write down where it's wrong.
exactly. So you erase them, you instead store the fix, right? The fix that you need compared to the predictor, and that's a zero free space.
Exactly, and that's polynomial.
And if you could not compress it, then
And if you can't
It's-
compress it, then you
it's
guarantee that
not
your
new.
distinguishers will good, right? Yeah, I mean, that's the whole purpose of doing these Bickerson stuff, but this is like, yeah, your compressor random argument that like almost black box ties. Almost. I mean, your distinguishers are exactly, if you don't fool those distinguishers. You know, if those distinguishers, if you fool those distinguishers, then you're just guaranteed that your set of walks is good enough to be used for a majority vote.
wait, where does the second distinguisher come in? Like,
Oh, because you need to know that actually you,
actually-
like, you took random walks all within the same thing, but if they all went to the zero and most of your walks lead you to the one. Like, there's some zero state that is within your collection of W walks, and a random walk actually always goes there, but your thing happens to avoid them most of the time. Then technically you have a good region of the graph, but not a good set of random walks. So you also have to check, you know, whether or not they behave the correct way at the very end.
is that possible? Okay, I know.
I mean, yeah, so if I give you, well, yeah, you can.
Oh, no, sorry, never mind, no.
Yeah, I mean, it's just a distinguisher, it's just like you output the one bit, which is the answer that you got. And then the question is, how does that behave on random walks versus on this, WI thing? You know, it's the first one is the trivial case where you know WI will always output true. But really, so that's more well behaved, but you don't really need that. If distinguisher one is to behave differently for WI versus a random string, that would already be good enough.
So you get the distinguisher, once, you get the distinguisher that you would get, right? Because it might not work, but then you check, does it correctly predict 50% of the?
Yeah, exactly. Right.
55% of the things, and if it does, then maybe actually it was pseudo-random, right?
But who cares?
Exactly.
Right, it's pseudo-random. It might have been pseudo-random, it's also pseudo-random. So, yes, no, certainly the whole point is you're gonna check your prediction ratio and then decide whether or not you're done. Whether you want or the compressed case. So by the way, we called this argument compressor random. Because first you check if you do this I compression, and if you don't, now you're in a real compressor random argument. As it was last month.
Oh, but that's also compressor random.
Exactly, it's compressor random.
It's not compressor random, it's compressor or something else.
Yeah,
Something else is a compressor random.
the first one we call the polytime.
No, but I thought it was compressor random or compressor random, I think that's the right.
Oh, no, because you either compress this one, or if you don't, then you are in this whole argument.
No, but that argument is also random, like the random thing would work.
Oh, sure, but the random case is the compressor random, yeah.
In a
It's-
sense, sure.
we're taking- Yeah, and then this,
Oh, I see.
yeah. So this, like I said, all of this, as it's been clearly demonstrated in the past probably hour. I'm not very familiar with this stuff. This is not my bag. This is like, I think, the new part of the paper. And again, there's a lot of cool combinations of that hashing. For example, in the non-deterministic world, you can talk about like double counting and trying to hit, like figure out how many states you've seen.
Oh, okay.
And techniques like that. This is like a really kind of weirdo argument, but it's, I think it's very neat, and it's kind of cool that this compressor random argument just then come back in with this hyper targeted compression algorithm that only fails when you already have what you want.
Nice. Okay,
Cool.
any more questions?
What do you say about double counting? I don't.
So you know double counting like shows you NL equals co-NL. Double counting is also a great way to avoid taking pseudo random walks and whatnot and actually just directly figure out how large your configuration graph starting at tau is. Right? Like you don't need any of this nonsense, but also this nonsense won't even work because if there's one, needle hiding in the haystack, you like getting decent walks isn't good enough for NL. But however, NL gives you this incredible power, which is double counting. So this whole technique works again in the non-deterministic world.
Great.
Great. Thanks.
Cool. Thank you.
audience